Nice. Okay, so this is going to be the 17th note in CS70. This one is going to talk about concentration inequalities and the law of large numbers. So to kind of introduce ourselves to these ideas, we're going to define an example and some terms and then go over some of their relationships. So let's say we're going to toss a biased coin. So P is going to represent the actual probability that we land on heads, and this doesn't have to be 1/2. And then N is going to be the number of tosses. This random variable S sub N is going to be the number of heads in N tosses. And then we're going to have this new variable right here called P hat, which is the estimate of the actual probability of landing on heads for our biased coin. So in this scenario, we don't actually know what P is. So we're just going to flip the coin a bunch of times, try to figure out what P could be. And that's basically what this is saying. We flip the coin N times, and we count the number of heads that we receive, and we divide that by the number of times we flip the coin, and then we get our estimate of the probability that we land on heads. So basically, if we flip the coin 4 times and we see 2 heads, then 2 divided by 4 would be 1/2. So we estimate that our probability of landing on heads is 1/2. Okay, and we're also going to have these terms right here, this epsilon and this delta. The epsilon is the error probability between 0 and 1, and delta is going to be our confidence level. And we're going to see what that means in a little bit. So first off, what is the expectation of the number of heads that we're going to get? Well, it's going to be N times the probability of landing on heads, right? So just using a similar example, if we flip the coin 6 times and the probability that we land on heads is 1/2, then we would expect to see 3 heads in 6 coin tosses, right? So now we want to know what is the expected value of our estimated probability. So we're essentially just going to sub in this equation right here. Yeah. And we can take the constant out, and we can just get the expected value of S sub N. We know that S sub N, the expected value is equal to N times P, so N times P over N is just equal to P. So the expected value of our estimated probability is equal to the probability. And just something intuitive, which we'll prove at the end of this note, is that the larger that N is, the more amount of coins that we toss, the closer our predicted probability gets to the true probability. Okay, and that's called the law of large numbers, which we'll look at the end. Now we're going to go over this. So this is saying, the difference between our estimate and the actual probability, is that less than or equal to our error term? And we can't always guarantee that this is the case, because our random variable it can take on a number of different values. So for example, if we toss the coin 6 times, there is a possibility that when we ourselves perform that experiment, we see 6 heads in a row. But it could be the case that the coin is a fair coin, that there should be a 1/2 chance of seeing heads. So now this kind of says something similar. And so because of that, we're going to relax our definition to this, which is saying that the probability that our estimated probability is off from the actual probability is less than or equal to the error. That probability should be greater than or equal to 1 minus our confidence term. So we have this confidence term that says that there is a small chance that we make an error more than epsilon, but there is a high chance that we don't make an error more than epsilon. Okay, so this is sort of the relaxed version of that, and we're going to arrive at this inequality later on, but something called Chebyshev's inequality, I think, yeah, shows that in the coin toss example, flipping the coin, this many times would be an optimal, like the optimal amount in order to ensure that this inequality is upheld. Okay, and that depends on our values of epsilon and delta. Okay, so now we're going to go over Markov's inequality. So, what is it? Just to define some things, we're going to have a random variable x. X is going to be non-negative. That means for every sample point in the set of in our sample space, when we throw it through the random variable, we're going to get some non-negative output. And we're also going to have this constant c. And what we're saying is that the probability that our random variable takes on a value that is greater than or equal to some c is going to be less than or equal to the expected value, or the average, divided by c. So intuitively, what does this tell us? So, we want to know what is the probability that our random variable takes on this value c. So if c is large, then that means it's not going to be very likely that our random variable takes that value on, because the expected value, or the mean, is that central point. But if we divide it by a large number, then this fraction is going to become small, right? And similarly, if our expected value is small, then the probability that we see something greater than or equal to c is also going to be small, just by this fraction right here. Okay, and so we're going to go over a proof. Are we zoomed in enough? I think, yeah. So we're just going to don't really know what this is called. I'll just call it the capital A. Denote the range of x, and we're going to consider some constant that is within A, I guess? Yeah, okay. So just using the formula for expected value, we're going to say that the expected value of some random variable x is going to be the sum of each value in the range of the random variable times the probability that that random variable takes on that value, straight from the definition of expectation. And we're going to say that this total expected value for the random variable must be greater than or equal to the sum of the same thing if we start at c. So for all a that are greater than or equal to c. Right? And then this itself must also be, this must be greater than or equal to this right here, because if c is like that floor value and then each value afterwards is greater, then this sum should be greater than this. Again, we know that c is a positive constant and x is non-negative, so we're just going to go up to some arbitrary positive top value up there. Sorry, I don't mean to get too into the weeds, but this is the same as if we just take the constant out and then apply the sum of these probabilities, and that's really just saying the same thing as the probability that our random variable is greater than or equal to c. Okay, and so given that the expected value of x is greater than or equal to c times the probability that our random variable is greater than or equal to c, it just takes the same form as this. You just do some manipulation and you're good. So if we were to plug in c is equal to 2 times the expected value, what would we get? So 2 times the expected value is 2 times the mean. It's like literally the same thing. So if we plug this in, we're going to see that the mean divided by 2 times the mean is 1/2. So the probability that our random variable takes on a value that is 2 times the mean, that's going to be a less than or equal to 1/2 chance, essentially. Yeah, it's no more than 1/2. Okay, and so we're going to look at an alternate proof. Alternate. Anyways, this proof is going to help us think about either the generalized Markov inequality. But again, we're going to have our random variable x that's non-negative and some positive constant c. And we're going to have something called an indicator value, which we sort of touched on before, but I feel like I probably defined incorrectly, or thought I was confused as to what it was. But basically, this is going to take in some statement. It's going to take on the value 0 if the statement is false, and take on the value 1 if the statement is true. So we're going to look at this equation first. This is saying that if our random variable takes on some value omega, that's going to be greater than or equal to c times the indicator function that our random variable takes on some value, and that's greater than or equal to c. Okay, so like, what does that mean? So if this is true, if x is greater than or equal to c, then this is just going to become 1, and this is just going to become x is greater than or equal to c, which, like, by definition is true because we established here that x is greater than or equal to c. Now, if x is not greater than or equal to c, then this side is going to become 0, and this whole equation is going to become x is greater than or equal to 0. And we know this is true because the random variable is non-negative. Also, I was just saying x when it was technically x omega. I mean, I think you understand. I mean, this says the same thing, what I just said. Okay, and now we're just going to obtain the expected values for each of these terms. And again, we can take out the constant of expected values. And if we recall from a previous note, 15 or 16, I think, the indicator well, so it's a random variable, right? The two values that it can take on are 1 and 0. Given that the expectation of a random variable is the sum of the value that the random variable can take on times the probability that the random variable takes that value on, as we saw up here, given that a is either 0 or 1, right? So, if it's 0 here, it's going to cancel out. If it's 1, then it's literally just going to be what is the probability that our random variable is equal to 1. So the expected value of an indicator random variable is literally just going to be the probability that the statement is true, essentially, that the indicator random variable takes on the value 1. I feel like I'm just saying a lot of the same things, hopefully in slightly different ways, to just solidify what the point is. So again, this turns out to be the same inequality. This is greater than or equal to this, which we can manipulate to look like that. Okay, this is probably a bit longer than necessary, but I think it's okay. So generalized Markov's inequality, we're going to let y be an arbitrary random variable with finite mean, and then we're going to have these positive constants c and r, and we're pretty much just saying the same thing. We're just going to have them raised. So it's going to use the indicator random variable again, and it's going to use a similar idea. So honestly, we can just I don't really know why this middle term is here. I think we can just look at this leftmost term and this rightmost term. So the leftmost term is saying that the absolute value of our random variable to the r is going to be greater than or equal to c to the r times the indicator variable. So, what is it saying? Is the absolute value of y greater than or equal to c? If this is true, if absolute value of y is greater than or equal to c, then it's definitely true that the absolute value of y to the r is greater than or equal to c to the r, right? And then if this is not true, then this becomes 0, and then absolute value of y to the r is greater than or equal to 0. Again, because we're taking the absolute value of it. It can be an arbitrary random variable, but we're going to take the absolute value of it. So it has to be at least 0. Okay, and then similarly, we're going to take the expectation of each term, See, they don't even take the expectation of this term. But again, we can take the constant out, and as we discussed before, this just reduces down to the probability that our random variable, the absolute value of our random variable, is greater than or equal to c. And then do some manipulation to get this. Okay, so I feel like I kind of went over the same thing 3 times, but I guess hopefully it's pretty solid now. So they kind of gave an example, like an example to develop a physical intuition for Markov's inequality, but to be honest, I still don't really understand how it connects. I don't know, maybe I was just fading at that point, but what is it? I can sort of explain the physical like this, but I can't really explain how it connects to Markov's explicitly. So, we're given this probability distribution, and we can physically think about it as the way we're distributing weight around this middle point, right? So we want the weight to be evenly distributed across the middle point, the mean, the average, the expectation. And, for Markov's inequality, we wanted to know kind of, what was the probability that our random variable could take on some value up here. In this case, we're just going to say that it's some multiple of the mean. So, as we sort of discussed earlier, if it's pretty high, if that value is high, then it's going to be unlikely that we obtain that value. So, I mean, that's, I think, the most important part of the piece of intuition you need to understand. This is saying something like, for every 1 unit of mass that you put on this side, this higher side, you have to add k minus 1 units of mass on this side. If you just think of it from a physical standpoint, I never took a physics class, but like this sort of intuitively makes sense to me. This is a distance of k minus 1 times the mean out. So this is a distance of k minus 1 times the mean out. This is a distance of just the mean. So if we apply a weight of 1 on this side, then we're going to have to apply a weight of k minus 1 on this side to kind of like apply the same amount of force on either side, such that this point is the center of, center. I don't know what it's called. But hopefully that makes sense. Okay, let's go into an example. So let's say we flip a fair coin n times. We want to know what is the probability of observing more than 3/4 times n heads, and we're going to use Markov's inequality. So just plugging in, we find that Markov's inequality tells us that it's 2/3, but if we use a formula to determine the actual answer, it turns out that the probability is nowhere near 2/3. It's actually very small for 100 flips. So in this case, the upper bound that this provides, sure, the probability is going to be less than or equal to 2/3, but it's going to be far less than or equal to 2/3. So, it's not super useful. So we're going to use something called Chebyshev's inequality to sort of refine our calculations. So, what is the definition? So for a random variable x, it's going to have a finite mean or expectation, and we're going to have a positive constant. So what this is saying is that the probability that the random variable, the difference between the random variable and the average, the probability of that being greater than or equal to c is going to be less than or equal to the variance divided by that c squared. So intuitively, what does this tell us? If the variance is small, then it's unlikely that our random variable will fall far from the mean. And again, that sort of just intuitively makes sense. But if c is large, if this distance from the mean is large, then the probability that our random variable is off from the mean by that much is small. The probability of that is small. Okay, so that's sort of the intuition. Let's get into the proof. We're going to define our random variable y as being equal to x minus mu squared. And just by the definition of variance, if we were to take the expectation of y, or the expectation of this term, that would just be equal to the variance of x. Okay? And something to note is that the absolute value of our random variable minus mu is greater than or equal to c. This expression right here, this is saying the same thing as if we were to just square both things and then just say it's greater than or equal to c. Or greater than or equal to c squared. Okay, so then, the probability that this is greater than or equal to c is going to be the same as the probability that this squared is greater than or equal to c squared. Okay? Yeah. So just kind of plugging in the values in using Markov's inequality, we can then expand out this expected value of y to just the variance of x as we defined up here. And you can also prove it again, this time plugging in r is equal to 2 for Markov's inequality. I think that would make for a shorter proof, but I'm just not going to do that. They also drop in a corollary which says we're going to define the so if we recall, the standard deviation is the square root of the variance of x, and we're going to say that the probability that our random variable is offset from the mean by some value greater than the multiple of our standard deviation, that's going to be less than that multiple squared. And we could just find that by plugging k times the standard deviation into Chebyshev's inequality. And I'm not really going to dig into what that means because I don't think they really discuss that. But I'm assuming this is useful and that's why they dropped it. But okay, so to kind of give a small example, so the probability of landing more than 2 standard deviations above or below the expectation is 1 over 4. I guess that's using the corollary. Yeah. So if we just input 2 into here, then this probability right here is going to be less than or equal to 1 over 2 squared, 1 over 4. So yeah. I'm not going to repeat myself, so that's pretty much what that says. Looking at the coin toss example, what is the probability that our random variable is greater than or equal to 3 over 4 times n? We're going to see that our expected value for our random variable is n over 2, given that we have a fair coin. And we can simply plug in this value. Let's see. So this is saying the same thing as this. We want to know if the probability is greater than or equal to 3 over 4 times n. This is that the random variable, offset by n over 2 is greater than or equal to n over 4. So this is like looking at one part, the part that it's greater than or equal to 3/4. This is, let's see. This is looking at, I guess, the other part. And then this, I think the absolute value for this is supposed to go here. And then from there we can calculate the variance of x divided by n over 4 squared. And I guess just using the binomial distribution, we can plug this in and achieve that for, yeah, so the variance just becomes n over 4 and then, okay. All right, so that's that. Let's move on to some applications. Okay, so if we want to estimate the bias of a coin, to just refresh ourselves on what we defined these to be, we're going to take the expected value of some, estimate of what the probability of landing on heads is, and using, the above equation, we get this, and this is equivalent to 1 over n times the expectation of all of those indicator variables, or the expectation that, the ith throw is a certain value, or heads, and we get p. So again, this is equal to n times p. 1 over n times p is equal to p. So now we want to, this is some of the expectations of the indicator variables. Now we want to take the variance of our estimated probability and just plugging in the same things. We know if we take a constant out from the variance, we actually square that constant. That's something they sort of just dropped in note 16 when they were talking about variance, I think. 15 or 16. And from there, we just want to sum up the variances of all the indicator variables. And we know that each indicator variable has a variance of sigma, I think. Sigma squared. Is that a sigma? Yeah. And so, sigma squared times n over this n squared right here is just going to give us the result of sigma squared over n. So basically the variance of p hat decreases linearly as n increases. That sort of makes sense, right? I think. I mean, this, as n increases, this goes to 0, like linearly. And let's see. Okay, so we have this expression for the variance, and then we also have, the expected value. So we can apply Chebyshev's, or I guess for the variance, and it comes out to this. And we can use some manipulation to isolate n. And let's see. So I think what I actually meant to put is delta, or what is this? Yeah, not delta. I meant to put sigma squared is equal to the variance of a particular random, a particular indicator variable, right? And so a particular indicator variable is just like the chance that we get heads on a single toss, and that is equal to the expected value of that indicator random variable squared. So in our case, that's going to be, that's simply just going to be p, right? Because the expected value of 1 squared is still 1, and then if it's 0, 0 squared is still 0. But again, because it's an indicator random variable, this expression becomes the expected value that x takes on 1, where 1 is squared. And so this is just p. This is just the probability p minus the regular, expectation of the random variable squared. So, as we calculate it up here, it's just p, and this essentially boils down to p minus p squared. If we take out a p, then we get this equation right here, p times 1 minus p. We just put this on top where the sigma squared is, and we get this inequality, and you can notice that we will maximize the variance when the probability that we land on heads is 1/2. If the probability we land on heads is much higher, then we're going to see more heads, and it's not going to we're not going to like fall far off from that mean as much as we could as if it was a 50-50 chance of being tails or being heads. There's hopefully intuitively that sort of makes sense. So that basically, yeah. So n greater than or equal to the maximum p to maximize variance, that's just going to give us this, which becomes this. And this is actually that first equation that we said we would look at up here. So what does this tell us? Let's look at an example. So let's say we want to estimate the probability that a person in the US is a Democrat. We're going to set our error term as 1/10, 0.1. We're going to set our confidence level at 0.05 or 95%. And then we're going to say take 500 samples or interact with 500 people. So Chebyshev's inequality tells us that, if we want to keep the error within 10%, such that we have a 95% confidence, then we need to ask 500 people, what their political affiliation is, to get an estimate that accurately reflects the political affiliations of the entire population. So, yeah, I think that puts things into perspective. So they gave sort of more qualitative example, which there were some equations there. I didn't want to look at them, so I just didn't. But I think at the end they kind of said say we try to find the wealth distribution of the U.S. Given that we have people like Bill Gates, that means that the variance is going to be really high, and it's going to take a lot of samples before we actually get someone who is that wealthy, because again, basically no one's up there on that side. However, if we don't account for those people, then our estimate is actually going to be very low. So just some sampling tips, I guess. Lastly, we're going to look at the law of large numbers pretty briefly. So what it says is we're going to have a bunch of indicator random variables. Actually, not necessarily. They're identical or independent and identically distributed random variables with common finite expectation mu. They all have the same expectation, and their partial sums are going to sum up to the number of heads that we see, for example, in this, if we use that example. And what we are saying is that the predicted probability, our measured probability, minus the average, is going to be less than the error. Let me say that again. So as n goes to infinity, the probability that our predicted probability offset from the average is less than our error is going to go to 100%. What this is saying is that, just generally, the more times that we sample, the more times that we flip the coin, the greater that our estimated probability will match the greater likelihood that our estimated probability will match the real probability. For an error greater than 0. So we're just going to take this equation. We're going to actually flip this sign because that allows us to use Chebyshev's inequality, and from there, just substituting values we went over, we're going to see n is in this denominator term, and as n approaches infinity, this is going to go to 0. But because we want to find this, we literally just have to take the inverse of that. So 1 minus 0 as n approaches infinity is just going to be 1. So just to say it for the millionth time, the probability of any deviation from the mean tends towards 0 as n goes to infinity. Okay. And that's all we have for note 17 in CS70. This has been all about concentration inequalities and the law of large numbers.